version of the ESIG Tucson Spring Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As you know, we canceled the physical meeting in Tucson due to the coronavirus situation, and we decided to proceed with a shortened online version. We started the series of 12 webinars in mid-March, and we're running through early May approximately twice a week. You can find the full schedule at the ESIG website under the Events tab. Recognizing the limitations of a webinar with typically more than 100 people on the line, we'll have individual presentations of 10 to 12 minutes, followed by a few minutes of discussion moderated by the session chair with hopefully some time for discussion at the end. The lines will be muted, so we ask you to use the question box in the lower right-hand corner of your screen. Today, we'll be hosting Session 4, DER Integration and System Operation, chaired by Steve Beuning. Steve's the Vice President of Holy Cross Energy. He has over 35 years of experience working in wholesale electric market design, transmission planning, and renewable energy integration. Steve is a previous president of the ESIG Board of Directors who put the wheels in motion to get us where we are today, and a good friend. So Steve, I'll now turn it over to you.
Thank you, Charlie. Can you hear me okay?
Yep, you're coming through good.
Okay, very good. Thank you. Well, folks, I'm really excited today to chair our session on distributed energy resource integration and system operations issues. We've got 4 good speakers for you today. I'm very excited and appreciate their joining us. Our first speaker this morning or this afternoon, depending which time zone you're in, will be Dr. Benjamin Kroposki. Ben is the Director of Power Systems Engineering Center at the National Renewable Energy Lab. He leads NREL's strategic research in design, planning, and operations of electric power systems. As the center director, he manages a staff of over 120 engineers and scientists doing research on power systems devices and on sensing, measurement, forecasting, operations and control, power system design and planning studies, and security and resiliency. Pretty broad mandate, Ben, and we're so happy that you can join us here today. Ben, I'll turn it over to you. And folks, if you have questions that occur to you during Ben or the other speakers' presentations, please enter them in the text box if possible, and I'll try and moderate that at the end of their talks. Ben, it's all yours.
Okay, thank you, Steve. Hopefully everybody can hear me. I'm going to give an overview today of what we kind of term autonomous energy systems. And really what we're presenting here is a vision of the future grid that's going to be integrating massive amounts of distributed energy resources. And I want to highlight some of the advancements we're making in this area to achieve this goal. So as we kind of think about the power system of today, it's really based and has been for the last 100 years on large central station synchronous generators like coal-fired power plants, nuclear power plants, gas plants, and hydro plants. For the most part, these systems are centrally controlled, and the generation is set up so that it follows demand. As we've moved to the future, we're starting to see a lot of new technologies integrated into the grid, and these will create additional challenges. I think a lot of people that participate in ESIG are very familiar with these, but let me highlight a little bit. We're increasing levels of wind and solar integration, so variable generation that's power electronics based instead of synchronous generator based. We're adding more additional communications, control, and data and information systems that can increase interoperability and cybersecurity issues. We're also seeing new distributed technologies like electric vehicles, household or building level distributed storage technologies, and also flexibility in loads start to become more prevalent. And then there's increasing interdependencies between the electric grid and other infrastructures like the natural gas grid. All of this is leading to a much more highly distributed and complex system to operate. So one of the questions we kind of get as we add in lots and lots of distributed technologies, is the grid going to get too complex to control? If you kind of take a look at the left-hand side of this slide, how we nominally operate the grid now, where we have central station bulk power generators. In the Eastern Interconnect, there's roughly 10,000 of these systems. And then we have regional transmission operators and local utilities that are sharing power and information. Typically, in some of those areas, we're running maybe 5-minute markets, and power flows are kind of adjusted using automatic generator control roughly every 4 seconds. That is then passed down to the local distribution utilities and serves the household loads. But as we start to add potentially hundreds of millions of distributed energy devices, we need to look at new ways of operating the system. And so one of the ways is a distributed hierarchical control approach that basically allows the entire system to be split into operational cells. And then these cells basically are solving real-time power flows and balancing amongst themselves. So what I'm going to walk you through next is a set of new research that we're doing in this space to actually bring this to fruition. So an example of this is a project we have that's looking at a really large-scale area. So if you can imagine the Bay Area fully deployed with distributed resources. And we're interested in distributed resources being generation, like solar, wind, fuel cells, local generators, energy storage technologies like batteries and ice storage, controllable loads in homes and buildings, and mobility through electric vehicles and charging stations. If we were to look at the Bay Area as an example, that grid basically has more than 10 million electrical nodes at the distribution level. If you think about the 4.3 million customers and each one potentially having local PV, storage, smart homes, plug-in electric vehicles, you have on the order of 10 to 20 million controllable devices just inside the Bay Area. And right now, we really don't know how we would actually optimize and control that many distributed operating devices in the grid. So as part of the projects we're looking at is kind of a bottoms-up approach all the way from individual homes to neighborhoods, communities, towns, up to the large city framework, and putting together a framework that enables scalable control and optimization across all of these levels. And we've been working on control theory and optimization theory to develop this, and I'll talk a little bit about that and then show how we're actually deploying this in real-world applications. But one of the key things is we're trying to show that these distributed control algorithms could work in real time, basically at second level across full large-scale systems. So in order to do this, we basically had to break up the math that runs behind control and optimization routines. So one of the big challenges that you have is the fact that the power grid needs to be able to operate in real time. So that means on a second-by-second basis, the entire system is always changing with power generation and loads coming on and offline. So to do that, you need basically a distributed control system as opposed to a central control system when you try to map this to hundreds of millions of devices. Another attribute would be that the algorithms need to be scalable. And so that for that, you need some type of hierarchical control structure so that you can run the same type of algorithms at a home and community scale as you would at a distribution scale and all the way up into the transmission level. And then also the entire way that you do control and optimization algorithms really need to be aware of the data and measurements available on the grid. One of the big challenges is the fact that you basically have time-varying asynchronous measurements, so not everything is nicely time synchronized into all of these systems for control. So as we look into distributed control and optimization, we've been publishing papers over the last 2 or 3 years. I won't go into these in detail, but if you're interested, you can follow up with the references that are listed on the paper that explain how we're able to do real-time closed-loop optimization of different systems of different sizes, and then also how do you bring into the fact that you are driving a dynamic system so that your optimization problems basically are going to be time varying along a time frame path. In addition to that, we're looking at ways of speeding up how fast these algorithms can work together. And so the idea of having a potential optimization problem be solved in a distributed manner, one way of doing that is something called alternating direction method of multipliers. That's basically taking a large optimization problem, splitting it into small subproblems, solving those, and then piecing it back together again. But we're also looking at things like adding in advanced artificial intelligence techniques like reinforcement learning to speed up the learning process from all of this data and information. And so we've been tying a lot of these different techniques together to then demonstrate how these would look on larger systems. So the first example that I'm going to show you here, unfortunately we can't run the movie there, but you can see the little link below. If you write that down, you can go find the actual movie that's running that I'll show you through in steps. But we've applied this distributed hierarchical control to, for example, a control of a large wind farm. So in a large wind farm, typically you have hundreds of wind turbines, all basically running in an autonomous fashion. Typically they're making decisions based on anemometer measurements that are located on the rear side of the nacelle or downstream from the wind turbine blades. And what you'll see in this particular slide is on the left-hand side of this, that's a typical wind farm control, and on the right-hand side is embedded these new distributed controls. So what happens is that over time, the wind may change direction. As you can see, the wind is starting to shift from left to right across the field. But the turbines on the left-hand side, you see, are still making independent decisions, and sometimes those decisions are being interfered with other wind turbines inside the wind farm. On the right, you see that the wind turbines are starting to move in a much more synchronized fashion. And as the wind moves around and then finally to a separate direction, you can see how well they mirror each other. The way we are able to do this is basically take the entire wind farm control system, break it into cells, optimize inside the cell, and through intercellular communication come to consensus on which way the wind is blowing, and then actually send communication signals between each of these operational cells. In this particular case, you're able to demonstrate that you can get a much faster solution from central control. In this case, central control would take about 13 minutes to solve this problem, whereas the distributed control algorithms could then do it in about 2 seconds. And this showed that we could get about 2% more energy annually across the wind farm using these distributed optimization techniques. So again, we want to take a look at how we apply this to the grid applications. So in this case, we're looking at a single distribution circuit and looking at, for example, how we could send P and Q, or real and reactive power set points, from a substation down to the distribution system that you've then set into these different cells. The cells can be physically designed or any type of design around what you're actually using as your cell, but you do need a coordinator inside there to receive the signals and then pass that to then the lower parts of the cells. As you can see, each cell is then broken up into smaller parts, and then you would be getting set points and then reacting to those set points and coordinating back to the higher level of devices. So in kind of a three-dimensional approach, you can see here from the top level, the larger cells would be receiving power and reactive power set points, passing those to the devices inside smaller areas, and then all the way to the smallest cell. Again, cells can be, they don't have to be a hexagonal shape as shown in here. They can be basically designed around however you want to operate and control the system. So then, if we go back to the large scale area, for example, this is a part of a project that we're looking at so that we can model the impact of all these distributed hierarchical cells in a large scale setting. So right now we're actually in the process of building this entire simulation in a high performance computer where we can actually model the interaction of tens of millions of devices wrapped inside this hierarchical distributed control structure. So that's all simulation, and that's nice, but most people really want to know, does this actually work in the real world? So we actually have set up the capability of doing this type of testing and evaluation in our energy systems integration facility, which is located in Colorado. Hopefully people, if they get a chance, once the coronavirus has passed, get a chance to come out and see some of the capabilities we have in this facility. But one of the unique things we're able to do in here is set up large-scale power hardware in the loop experiments. And as an example of that project, we actually set up an entire experiment that's running on a single large simulated distribution feeder, but we have up to 100 actual controllable assets. So they could be things like the electrical vehicles that you see here in the picture, PV inverters, battery energy storage. We also use local loads, residential scale loads, and appliances, all with control algorithms to mimic what we were showing you before in the simulation. But as we have just finished this experiment in January, it's, as far as we know, the largest ever power hardware in the loop experiment that ties 100 different devices into a simulated distribution circuit, all running these advanced optimization and control algorithms. I know there's a YouTube video out there if you want to see some more information on this particular project. So let's look into the future. So as we think about the future and how we can deploy this in larger scale, we're looking at things like entire cities. In this case, that blue line circle represents maybe a centralized control that you would normally have on systems across a city. As that goes out, maybe you're trying to control voltage and the voltage profile isn't where you want it. So one way we're looking at this is taking this entire city concept, splitting it into aggregated cells or cellular approach to do, in this case, optimization of voltage. And the little cells then communicate with each other and provide a more optimized voltage profile for distribution circuits, as an example. Again, this is a cute little video that you can find on YouTube to see it in action. So at the end of the day, one of the things that we're trying to do is build and verify that you can create an entirely end-to-end scalable approach to grid operations that include things like buildings, mobility, wind and solar plants, tie all this together to allow integration of all energy sources, confirm that you can actually create scalable control signals that go across millions of devices, provide opportunities to do real-time operation, and integrate asynchronous data and communication systems. So across this entire space, this is what we're interested in trying to prove, and this kind of ran through very quickly a lot of the new research that we've been able to develop and deploy across this system. So with that, I'll say thank you very much, and I don't know if we're taking questions now or if we are doing them at the end.
Hi, Ben. This is Steve Beuning. We'll take questions now. Good news, you got several that were generated during your talk. First one came from Gerald Keenan. He says the Northwest Power Pool is concerned with distributed resource risks of tripping due to frequency excursions that could potentially increase net load at the grid level to the point of under-frequency load shedding. Have any ride-through standards or anything address this?
Yeah, so actually the new updated IEEE 1547 interconnection standard for DER definitely allow DER to, I would say, perform better and give a wider operating range for both voltage and frequency excursions. This is definitely a hot topic out in Hawaii, where they have a huge amount of distributed solar integrated with their grid and need to coordinate that with their under-frequency load shedding schemes. So a lot of the new updates to IEEE 1547 address that specific issue. And so I would recommend taking a look at that document and then adjusting what you need to make sure that your distributed resources deployed in your area are not interfering with your under-frequency load shed schemes.
Thanks, Ben. The next question is from Hassan Idris. What level of control should, my thing just moved on me. level of control should the utility, if at all, the consumer end of autonomous energy nodes? Who sets the control metrics?
Well, it looks like Rick's going to answer that question for us in the next presentation, but I will say that this is still open for debate. And I think at some level, what we're trying to do is provide, and the research I presented was provide a way to just push generic power and reactive power information down and then measure what the devices are doing back. So there's not like direct control per se from a central level. I don't think we'll be able to achieve that, but we do need to find a way to push some type of signal down to devices and then let them react and then measure their reaction and then understand how those coordinate together.
Okay, Ben, thanks. Next question was from Wendy B. Is the control on the wind farms that you showed, should that be something provided by the manufacturer or the grid operator?
Well, in that particular case, that control where you're trying to optimize wind plant power output, that's probably should be provided by the wind manufacturer, the wind plant manufacturer. But what we were just showing there was the concept of how you take a large, complicated system, break it into these smaller components or cells, and have them self-optimize and then get a better overarching solution. So the specific example probably would be implemented by a manufacturer, but if we were to apply that concept to the grid, then you may need the grid operator to do that at a higher level.
Thanks, Ben. Next question for you came from John Simonelli, and Rick responded in the text box that he thought he'd answer that question in his presentation, how the operational cell concept might differ from the DSO concept in areas like New York. And John had a follow-up question, which was, how would you optimize the interchange between each individual operational cell? As an example, each individual cell cost being optimized or an overarching system cost optimization?
Yeah, that's a good question, because you got to, what we're at least thinking is that individually inside the cell, it's trying to optimize the individual cell costs or performance as much as it can, but still it does need to be getting some kind of instruction from a higher level as to what are the constraints or the system-wide optimizations that it should be taking into account. So this is a back and forth thing, and as you realize how the grid operates, it doesn't just stand still. So you're having to come to real-time optimal solutions as quickly as possible, but then they're changing on you in time. And so you're really tracking trajectories as opposed to specific, absolute optimality in the system. But you do need to take both your local constraints and optimizations and a higher level so that you're not impacting overall system operations.
Thank you, Ben. There's light at the end of the tunnel. I think we're down to the last two questions for you. Thanks, everybody, for all of the engagement and feedback on the presentation. This next one is from user Tom Acker. Assuming the autonomous distributed energy controls work well, what business models do you foresee implementing this technology, for example, at the ISO or utility or aggregator level?
Yeah, this is definitely a challenge that needs to be thought about and worked out, is how would you create business models around this? I still think that what we were kind of showing is what you would see a utility implement, and they could push this back up to the ISO level if the ISO wants to run this way or not. The big challenge I think you have right now is how people are doing aggregation. And whether or not it makes sense for how the system operates. So if you have distributed assets that are being aggregated, say, by type, as opposed to by physical location or things like that, then those may impact the system operations and give you some unintended consequences. So if you were aggregating all air conditioners of a certain manufacturer and they were responding a certain way, but that wasn't taking into account any of the local constraints, that could potentially lead to some challenges and problems. So I think that still needs to be worked out, and a great conversation to have inside this group.
Very good. I'm going to cut off the questions after this last one because we do have the other speakers that we'd like to do. If we have time at the end, we can come back to some of these that we may have missed. But Ben, the last question for you is from Jared Wright. He asks, does NREL envision running the main campus in Golden in a similar manner as described, as a result using it as a real-world living demonstration for the approach? He says they have some similar thinking for their campus there in South Africa.
Yeah, so as I showed you the demo that we did, it was actually in the lab, so under very controlled conditions. We actually are rolling this out to the real world, although not yet at the size of our campus. We are actually working with Holy Cross Energy to deploy these on a group of smart homes in their service territory. So it's the same control algorithms are getting deployed on that set. It's called the Basalt Vista set of smart homes in Holy Cross's service territory. I think there's some information that you can find on the website about that. But we are definitely looking for how to deploy this into real-world applications for better demonstrations. Hopefully, we'll eventually get back to our campus and deploy it across our campus. All right.
Excellent. Thank you so much, Ben. We all really enjoyed your talk. I'd like to shift gears now and switch to our next speaker, Rick O'Connell, GridLab. Rick is the executive director. GridLab is a national nonprofit that gives technical grid expertise to enhance policy decision-making and to ensure a rapid transition to a reliable, cost-effective, low-carbon future. GridLab delivers technical assistance to advocates, regulators, uses a connectivity platform to facilitate knowledge sharing and education on best practices for complex grid issues. So Rick, I'd like to turn it over to you. Thank you, and look forward to your talk.
Great, thank you so much, Steve. I'm super glad to be here. You know, this is the first time Charlie has invited me to speak at an ESIG event, and of course, I'm now speaking on a webinar. So hopefully correlation is not causation, and the next time Charlie invites me, we won't have a global pandemic. That being said, I think I'm glad that I'm going right after Ben, his excellent presentation on the work that NREL has been doing on autonomous energy grids. I'm going to try and address the sort of broader question, which is, what is the communications and control architecture for DER that maintains reliability on the distribution grid and unlocks grid services both for the distribution system and for the bulk system? And I'm not going to pretend that I'm going to answer this question in the next 15 minutes. And I think that, you know, Ben's excellent presentation showed that there's lots of different thinking around this. And I just want to sort of talk through why this is an important topic right now, what's happening right now with 1547 and other things. I think a couple people made really good questions, asked really good questions about DSOs, distribution system operators. So I think this is an important question, and we're at an inflection point, and it would behoove us to be thoughtful around this. For those of you aware, last May, ESIG had a really excellent workshop, two-day workshop in Denver, where we looked at the roadmap to 100%. And Ben and myself and others were part of the DER work group. Ben actually led that work group. And this was really the main topic of conversation around how we were going to get DERs to provide services. So I want to dig into this a little bit more. So I think Ben already sort of covered this, like why is this important? You know, DER is not just rooftop solar anymore. It's really including, now we have demand response, we have electric vehicles, we have storage, we have to, you know, and now we have smart inverters, and I'll talk a little bit about 1547 coming out. So we now have communications enabled to these devices. And we also have technology that means that we have low-cost communications and control are now possible, right? You know, a lot of you will remember the sort of old days when, you know, companies put like an old RF box on your air conditioning, and sort of cycled your air conditioning, and those systems were quite expensive. Now we have sort of everything comes internet connectivity enabled, and so we have the opportunity to do that. All right. So where are we right now? Why is this time important? So we have our 2 states in the US, at least, California and Hawaii, that have pretty high penetrations of DER, about 10x, I think, of other places, have been early adopters of smart inverters. So in California, that's Rule 21. In Hawaii, that's 14H. So they've got experience with deploying inverters that have communications capability. And then IEEE 1547, 2018, as Ben mentioned, is coming. So we're going to get equipment certified to 1547, 2018 by the end of this year. It includes communications capabilities, right? So all of those devices have to be capable of communicating. On the wholesale market, we have some wholesale DER products. So places like CAISO, New York ISO, ISO New England have created wholesale DER products, or ability for wholesale aggregations of DERs to connect to wholesale markets. Haven't seen a lot of traction. It's still pretty early days. And then we've seen some virtual power plants. So things like non-wire solutions, providing aggregations of DERs, providing distribution level services, as well as some wholesale services like Sunruns and ISO New England providing capacity. So we're kind of on the cusp, I think, of DERs really kind of growing up and getting new technology, sort of being seen as this kind of behind, customer-sided, energy-only generation, and now actually becoming like a sort of full-fledged member of the grid. But as Ben pointed out, like, we have some assumptions underlying this deployment of DER, and I think there are I would really split things into 2 camps, right? And those camps are kind of control and autonomous. And in the control camp, I think there's a lot of folks, especially the distribution utilities, who just sort of have an assumption that if I'm going to deploy DER widely on my distribution network, I have to have control, right? And that's typically kind of a centralized control paradigm. I have to have control. I have to have communications control of these devices to maintain reliability. And I think to date, a lot of the focus has been around the effects of distribution reconfiguration. So when you reconfigure your distribution circuit, as well as some concerns around anti-islanding, concerns that DER might island, even though might create unintentional islands. I think on the other hand, we have the autonomous approach, which I think Ben laid out. Autonomous means many things to many people, but the autonomous approach is, hey, these DERs, these smart inverters have intelligence. They can make decisions in real time around how to respond to signals like voltage, frequency, and I think, as Ben sort of talked about, potentially other signals. So respond to day-ahead market prices, real-time market prices, other signals that we might want to send them so they tune and do respond the way we want them to respond. And I think that's sort of the way California and Hawaii have gone. So they've deployed smart inverters, but they haven't used the communications capabilities yet. And they're not using those. They're still basically deploying autonomous controls at this point. And I think other states like Illinois and Minnesota are kind of following California and Hawaii. So these are kind of the 2 camps. And let me first just sort of talk about why people would want control, why distribution utilities would think that control is a good approach. I think some utilities sort of think the set it and forget it approach on voltage regulation is not reasonable and acceptable, and that the voltage profile of circuits will change over time, over the years, and that they will need to tune the DERs to provide the right voltage profiles. And they also sort of feel like when circuits are temporarily reconfigured, they're going to need to also change those voltage profiles. I think there's still concerns about unintentional islanding, even though it's 2020 and the standard's pretty clear that it's not allowed. I think a lot of utilities are still nervous about unintentional islanding, and they want kind of redundant control to be able to turn off DERs. And I think there's also a concern around the T&D interface. So there's distribution utilities that are concerned of, that they have DERs on their distribution circuits that are responding to wholesale, maybe power prices or even wholesale market controls that they don't understand, and they don't have, that those external controllers don't have visibility into potential distribution congestion. So that's sort of the control approach. I think the autonomous approach, I think the first thing I just want to acknowledge from Ben's presentation is that you have to be careful. The control approach, if you go down the pathway of that, you have to be able to be willing to centralize control tens of thousands, potentially hundreds of thousands, potentially millions of devices. And I don't think a lot of folks have really thought that through. Right now they think, well, I've got 10,000 DER in my service territory. I'm going to control those 10,000 DER, and I've got some growth rate, but they haven't sort of thought through what happens when I have a million. Will I have enough computing power, and is that even a tractable problem that I can solve? And I also think that reliability really moves at the speed of physics and isn't going to wait for a 5-minute market signal or even a 4-second control signal. And these DERs have intelligence and can respond intelligently to voltage and frequency, and generally be trusted to do the right thing if they're set correctly. I also think the cost versus the benefits of control is a little bit tricky. It's expensive to create a communications and control architecture. It's not just the cost at the device or the cost of the control communications. It's also the cost at the back end of building a DERMS and actually being able to make it useful. Sophisticated utilities like PG&E sort of may have made decisions after doing some pretty sophisticated DERMS pilots that they decided that DERMS really wasn't ready for prime time. And I think there's also a market concern. I know a couple of folks have asked questions about DSOs. I think both Ben and I are really focused more on the technical communications architecture, but I think as we move into a DER-heavy world, and I know a lot of folks like Lorenzo Christoph, New York, have really been thinking about this distribution system operator concept. I think there's also not only we're going to have to rethink our communications and control strategy, but we're also going to need to think our regulatory strategy. And I think, as we move, there's concerns now if distribution utilities instrument and control DERs, are they now going to then say, well, I'm the best person to aggregate these devices and bid them into markets and become the market operator? And maybe that should be left for third-party aggregators. So there's some intersection, I think, of sort of the technical issues with what's the regulatory. It's not just the communications and control architecture. There's also a regulatory architecture. So this is my last. These are some sort of early ideas around principles of like where we can go now, and like why it's important now is because 1547 is coming. States are making decisions about how they're going to implement 1547 and how they're going to implement smart inverters. Obviously, some states like Hawaii, California, Illinois have already started deploying smart inverters using the 1741 SA standard. But what are some of the things that we should be thinking about going forward so we can get to, I think, Ben's really excellent vision of this more sophisticated control hierarchy? So I think first is that, given what we know today is autonomous makes the most sense. It's working in high penetration states like California and Hawaii. We have autonomous voltage regulation. We could even use something like Volt-Watt as a backstop for if there is real concerns around voltage congestion. I just don't think that we need redundant control for unintentional islanding. I think that issue has been beaten to death over many years. Another option we could think about, and sort of as an interim until we come up with a better overall strategy, is maybe we just implement communications for larger systems only. So this is something like what Germany did, where they said, you can get to, 80% of your megawatts with just 20% of your system. So they only instrumented systems 100 kilowatts and above. Other interesting options to sort of solve, like T&D pricing, I think some creative ways to do this. I think New York ISO is looking into ways to sort of have the distribution utility kind of rebroadcast market prices, but include distribution congestion in that pricing, so that there's ways to do through sort of passive signals to like let DERs know about the state of the distribution network, and that doesn't have to be sort of a command and control. And then in terms of, from a less technical and more regulatory perspective, I think at least in the near term, it seems to make the most sense for allowing market participation through aggregators and not necessarily through the distribution utility. Because if we do move to something like a DSO, right, the DSO is not a market participant. It's a non-market participant like an ISO that just manages the distribution grid for customers. So that's all I have. I think it was well done to Steve for putting me right behind Ben to sort of talk more broadly about some of the questions that I think we're going to be facing in states around the U.S. as we roll out 1547 and start thinking about what's the architecture that's going to be able to unlock grid services as we maintain reliability on the distribution grid.
Thanks so much, Rick. I appreciate it. For those that have questions for Rick, you can enter them in the text box. Rick, I had one for you to get things started. It's probably not sexy to talk about energy accounting because that's such a mundane part of utility operations, but it's really mostly unchanged from 50 years ago. And I've heard people talk about things like blockchain, and to what extent do we need new techniques for energy accounting going forward to address this potential world of millions of devices interacting in a commercial manner?
Wow, that's a great question. Steve, you had to ask the blockchain question, didn't you? Honestly, that's not something that I've thought deeply about. I mean, I guess maybe I can give you a non-answer on that and say that I think energy is going to be less interesting going forward, and we're going to be more, I'm more interested in thinking about like how we're going to measure the health of our distribution system and new metrics for measuring the health of the distribution system. I think metrics like SAIDI and SAIFI are really outdated. And so, like trying to figure out some kind of health metric. And then I think also just thinking through, energy being a less interesting commodity. And so how do we let DERs provide, these other values that are kind of about moving energy, how do we value moving energy around in time? Like if I'm an EV and I charge at a different time, there's value in that. I mean, the energy value is the same, but I've moved that energy to a different time. The sort of the passive capacity product that the Sunrun ISO New England example, I think is really interesting. And so that's not an energy accounting issue, but more, how do we create new products, market products that DERs can plug into and provide grid services is, I think, something more interesting than sort of accounting for the energy.
Okay. Thank you, Rick. That whole settlements processing future will be an interesting piece of this as well. I appreciate your thoughts on that. I don't see any other questions in the box at this time for Rick, so let me introduce our next speaker, Matthew Richwine. Matthew is a founding partner at Telos Energy. He's self-described as passionate about power systems engineering, power electronic controls, and system stability. That's a small set of people that fit into that category for passions, and I appreciate that about you, Matthew. 10 years, he's been designing, testing, and analyzing thermal and renewable power generation equipment and studying the stability of power systems ranging from tens of megawatts to tens of gigawatts. So with that, I'd like to welcome Matthew and take it away, please.
Thanks, Steve. And thanks, Ben and Rick, for setting the stage here. What I'd like to talk a little bit and share this afternoon is pulling on a thread that came up particularly in Rick's discussion and presentation about control, and specifically the Volt-Var control on the distribution system. So one of the things I want to talk about is a specific aspect of Volt-Var control, that being the small signal stability, and we'll get into, what am I talking about exactly there. And then what do we know from transmission system applications? So, my background is more at the transmission system level with utility scale renewables, connecting to high voltage circuits, and basically en masse in hundreds of megawatts systems. And so when I've been getting into this distribution level applications of these for these much smaller systems, trying to look at and see where are there things in common and what lessons and risks can we take from the transmission system, and see and really go in with an open mind on the distribution side to say, is this a potential risk on the distribution side, and what mitigations may be available, and how do we avoid stepping in some potholes along the way. So that's jumping in here specifically to a small signal instability. So talking about the grid stability of the system, in particular power electronic devices on the grid. And so as we all know here, grid stability has many facets. Oftentimes they're lumped into kind of a grid stability label, but then I like to parse those into a number of different ones so that we can be more specific about what we're talking about. And so, for instance, small signal stability, large signal stability, to me, I think of these as kind of control stability aspects. And then there's voltage stability, angle or transient stability, and frequency stability, which are more of the system level stability aspects. And I don't think, that's not a comprehensive list. But what I really want to zero in on today is the small signal stability. And what I mean here is talking about small deviations about an operating point. So in the case of Volt-Var controls, you're generally operating around nominal or maybe a little bit higher voltage, and the deviations in terms of voltage and the active and particularly reactive power flows around this nominal set point. And so to try to illustrate that a little bit, the two graphs on the upper hand in the upper right of this slide, talking about plots. So these are just showing kind of representative active power and reactive power plots, where you can see in large signal stability, you're actually covering a large range of the operating region of the equipment. There's lots of nonlinearities that can happen in there, and mode changes and such, versus small signals in stability, where you have small changes. To some degree, you can linearize about an operating point. And so this in particular is relevant to the Volt-Var control. Volt-Var control is a closed loop feedback controller. And any closed loop control system has the risk of going unstable. It's just a question of at what point, under what circumstances does it do that. And the control loop that I'm talking about, without going too far into the weeds here, but at a relatively high level, in the diagram at the bottom, so we've got two key components. There's the inverter component and the grid component. And the inverter applies an effort to the grid, in the case current or reactive current, reactive power. And the grid produces a response in terms of it responds with voltage. That voltage is measured by the inverter and fed back into the controller, and generally attempts to follow some desired set point, which could be flowing from anywhere, and I'll kind of leave that open for now. And in this situation, now that you've got a closed loop controller, the feedback can be self-reinforcing or positive and destabilizing, or it can be self-correcting. And so that's what I want to dive into a little bit more. So taking a page from the transmission system briefly, just to provide some context. This small signal stability of Volt-Var control is nothing new to the industry. We've been dealing with it for many years with renewables, with conventional sources at the transmission level. And so by way of just showing the diagram, the transmission system, there's a couple differences I'd like to point out, or key points I'd like to point out. So you've got, in this case, there are two generating systems, aggregate, right, each composed of many modules of some inverter-based resource. There is a Volt-Var controller that is local, that is measuring some voltage node, usually at the high voltage point of interconnect, and providing providing control to the inverters, or providing direction to the inverters, which are then injecting VARs to modify that voltage. And this can happen in many places, and then it's all grid interconnected, and typically the load is distant, so you're transferring the power over some long distance lines to the grid. One of the things about that we focus on is the weak grid issues, commonly quantified by short circuit ratio or the grid strength. And you can see in the plot on the bottom left, a normal behavior where if you have for instance, in this case, a line switching event where you're doing Volt-Var control and you have an event, you have a little bit of a second order ripple that is damped out quickly and you have no problems. For the same control, everything else constant, but a change in the grid, particularly in the grid strength, for instance, a transmission contingency that weakens the grid. For the same line switch event, you can now see some of that unstable behavior starting to manifest in terms of sustained oscillations that are not damped out. This is a small signal stability that we have paid a lot of attention to avoid and to mitigate on the transmission system. So the question is, okay, does this apply in the distribution system context? And noting a few key differences. So in this example, this distribution circuit is highly simplified in terms of just looking at a couple of these factors, still just two generators. The network is it's a low voltage network. Therefore, the X to R ratios tend to be much lower than we see on the transmission system. There's also load is integrated in the circuit and much closer to the generation source, at least for instance for solar PV that's integrated in with the loads. And there's some degree of local damping from those loads. Also, there's a lot more inverter variety at the distribution level than what we're used to seeing at the transmission level, where there's kind of a handful of manufacturers and each have a handful of products running similar control algorithms. On the distribution side, the market is just much more varied. How that becomes a factor is, I'd say, yet to be determined. So looking at specifically what is the industry laying out, what is the direction for Volt-Var controls, and drawing on 1547, the most recent revision, which provides a framework for the response and a range of possible values that could be used. And pulling on a couple leaders in the space, California Rule 21, Hawaii Rule 14H, have laid out some parameter sets for that I've seen others start to pick up and adopt and carry these forward. Zeroing in on these particular curves, and also what's not shown on here, but there's a note on the response time tuning of these types of controls. Those I see are the dominant factors in terms of the inverter behavior piece of the system. There is a note, IEEE notes here right in the documentation, that improper selection of these values may cause system stability. And I suppose this is really the point of my presentation today, is just to highlight this and expand on it a little bit. what do they mean here? And this is, to me, this is a very important footnote. So distribution system stability, how I looked at it was to do a few simulations of dynamic simulations with detailed models. Note, I've seen dozens of reports on Volt-Vars, control and distribution systems. Most of these, in fact, all that I've seen, are looking at steady state or quasi-steady state simulations. They are essentially a series of load flows. They are not capturing the dynamic behavior or these relatively short-term stability issues. They are just looking at different snapshots in time throughout the course of a day. That's a very different kind of study approach. What I'm focusing here on is the dynamic behavior, the stability over seconds of operation. And the four key factors that I see here are, one is the gains. So on the inverter side, the gains of the controllers. That's effectively the slopes of those curves that are specified and using the framework provided by IEEE 1547. The response times, number two, this has to do with the inverter's regulator tuning, how fast it's going to achieve a set point if it were, for instance, given a step change. Three, the grid dynamics and behavior, the grid strength, the damping, the extra R ratios in there. Effectively, what we describe as the driving point impedance of the grid that the inverter sees. And then fourth, the communications latency. And so, Ben and Rick were talking a lot about communications. What I mean here in particular in this communications is the communications that's in this control loop. So it is the measurement feedback to the inverter of the voltage measurement. That this could be integrated, or there could be a plant level or a small plant level control that is then sending commands back to the inverter modules. The latency, the delay time from this is a critical factor in the stability of the system. And so looking at, and really this is just dipping a toe in to see, does it deserve a closer look? And so I'm just sharing a small subset of a few simulation runs bearing a couple of these parameters. Looking at the top traces on the left and the right, this is a simulation with relatively low latencies on the communications. And it is, again, for a switching event. So we're not talking about faults. We are just talking about a small signal stimulus in terms of a switching event that's happening kind of out on the grid. In this case, on the 34.5 kV network that's modeled. And the effect of the load. So in this first case, there isn't the local load I've eliminated to kind of test and see what's happening. And you can see the sustained oscillations for this particular grid strength, which it is a relatively low grid strength condition. There's a high penetration of inverter rating on the grid, given the strength of the grid that it's connected to at the station. Introducing the local load in this case is a benefit in terms of, you can see that there is more damping in terms of the oscillations decay away. So that seems to be a positive factor here. That's generally expected, what I would have expected to see. On the bottom, introducing slightly higher latency in the control loop feedback, so basically removing some stability margin. And you can see, again, without load, so on the bottom left-hand chart, you can see the instability is, again, manifested. It's slightly higher magnitude in terms of, you see the reactive power changing a little bit more than it had before. And then with the introduction, again, of local load in this case, modifying the grid dynamics. So it's changing that driving point impedance of the system. And in this case, it's actually causing more oscillatory behavior. Now, I don't want to oversimplify this or draw too many conclusions. Really, there's more that needs to be understood here. And there's a number of factors that go into that in terms of the topology of the network. So to conclude, there's known stability risks on the transmission system. These concepts still apply to the distribution system, but there's a lot more complexity here. The distribution system, it's evolving from a supply side and the load side. I didn't focus much on the loads here, but they are becoming more and more power electronic as well. Variable frequency drives on most of the air conditioners. And so I think the message here is to be aware of the new risks from a number of these factors coming together, and just to make sure that these approaches, which I think have a lot of power and utility, are just applied carefully so we don't cause any unforeseen issues. Okay.
Excellent, Matt. Thank you very much. Anybody has questions for Matt, they can enter them in the text box on their screen. I guess there's one here from Michelle Rozier. She says, Matt, have you looked at a dynamic simulation where the grid has line voltage regulators or other regulation equipment? If so, what was the impact on the instability at various latency speeds?
So that's a great question and a natural follow-on. The short answer is no. I haven't looked at that, but that is a natural direction to look at those other devices, whether it's voltage regulators, tap changers, switched caps. All of those things are going to play into this, maybe in slightly different time frames. But yeah, that's something I would like to get to.
Excellent. Matt, another question for you. Do you see increasing use of phasor measurement units, PMUs, at utility subtransmission and primary secondary distribution levels? If so, how soon?
So I'm probably not the best. I'm not the best to answer, what the deployment looks like of PMUs down into into the distribution system. I'll defer that to someone else. But what I would say is that PMUs with 60 hertz sampling, they should be able to provide some visibility of these phenomena. So if that data was available and is deep into the system, I would think it would be useful for detecting and staying on top of these potential risks.
Thank you, Matt. And I see Ben Kroposki added a comment into the text box saying, in response to Michelle's questions, that voltage regulators typically have a 30-second delay built into their control hierarchy to reduce control interaction issues.
Right. Regulators, yeah, there are delays, but what you could see is potentially, depending on how things are coordinated or not, that in the time between those mechanical changes, tap changes, the Volt-Var controls of the inverters do something else and cause it to switch back, and you can have I'd say there's a potential for toggling if it's not coordinated.
Matt, one other question. A key component in any stability simulation is the load model. Are you using the NERC recommended composite load model or something else?
So the load model here, and that's a very good question, was very simple. It is just a passive load model. These were actually performed in PSCAD, so this is EMT. But yeah, the intention to draw on this farther is to look at the impact of induction load models, induction motor as parts of the load model. Yeah, I think the load model is another really important factor here.
Thank you. Next question I see is from Mahdi Hajian. He asks, do you see a need for using EMTP models for distributed resources in the near future?
Yeah, That's a good question. I wouldn't want to make too general or broad of a statement about that. There's a number of challenges. For EMT models have a number of advantages and disadvantages in terms of course, the advantages, they capture the full detail and the control algorithms that are otherwise kind of only approximated in the phasor domain tools, but they're much more difficult and complex and computationally intensive, and the data inputs are much bigger. So there's a lot of challenges. What I think the approach is to really continue to find representative feeders and simulations and do some deeper dives with some more detailed tools in a more surgical manner. I wouldn't advocate for kind of a massive study of distribution systems in EMT.
Thank you, Matt. One question from Wade Du. He asks, Matt, do you think if a phasor-based simulation can reproduce PSCAD or EMTP results?
So it depends on the phenomena being studied. For the Volt-Var phenomenon, for these types of interactions, I do think there's, I chose PSCAD for kind of a couple reasons. Part of it was convenience on my end, but these regulators and controls can be adequately represented. The Volt-Var level controllers can be adequately represented in phasor domain models. So I wouldn't discount that.
All right. Yeah, thank you very much for your presentation. That takes us to the end of the questions that we had in the box. So with that, I'd like to shift us over to our last speaker for the day. Ted Burhans is the Director of Emerging Technology and Innovations at Tucson Electric Power. His responsibilities include oversight of renewable energy, the Renewable Energy Department, including residential and non-residential distributed generation programs, as well as utility scale planning. He also has the Residential Energy Efficiency and Demand Side Management Department and the company's innovation team. Ted has been with Tucson Electric Power for the past 13 years, holding various positions mainly in the renewable energy area. He has a BS in Engineering Management from the University of Arizona, and an MBA from Ashford University. So Ted, thank you for being part of the webinar today, and I'd like to turn it over to you if you're ready.
Sounds great. Thank you, Steve. Hopefully everybody can hear me okay. So that was an excellent introduction, and actually I'm very pleased that I'm bringing up the rear in this one. There's been a lot of great conversations and topics that have been brought up, and I want to give you guys an overview of a project that Tucson Electric did in partnership with EPRI, about a year and a half long project through 2018, 2019 called Project RAIN, Resource Aggregation and Integration Network. And the way that this presentation is set up, it's we kind of go over the overview of just what the research project looked like, kind of some of the set points and how we conducted the research, and then some of the results, both graphs and then some just anecdotal information that we got out of it. So first off, Project RAIN was really looking at how we could aggregate 5 different types of DER technologies. So you see PV systems, EV chargers, battery storage, thermostats, and water heaters. And bringing all that in together into a DERMS platform. So in 2018, when we set out, we said, what is the actual state of DERMS platforms in the utility world? So that was one of the main questions. Then we also had, what are the practical capabilities of individual and aggregated DER? What's the potential for customer engagement in supporting the grid? What are the challenges of communication and coordination? And then what are actual strategies for applying DER management to TEP systems? So of the 5 different technologies, we actually were able to deploy about 45 different nodes. So we worked with customers who were previously, or not previously, but are still on our Tucson Electric Power owned rooftop solar program. So these are customers, in total it was 12 customers, and TEP actually owns their rooftop solar. So the inverter is on the utility side of the meter, so the customer didn't have necessarily a financial impact if something were to change based on how the PV was outputting, such as that. So we were able to deploy, like I said, to 12 customers of ours, and we tried to put in 3 different technologies at each site. So 6 customers received a battery storage system, 6 received a heat pump water heater, and then they had the PV system already, and then a thermostat. In addition to that, we also used our own utility headquarters, and we used the identified the electric vehicle EV chargers that we had there, as well as the 50 kilowatt PV system that we had there. So that's what made up about 45 different nodes across the entire project. So this is just a schematic of how we set things up. We had, like I mentioned, the 5 different types of technologies. One of the big pieces of the project was we really wanted to try as much as we could to use open standard communication protocols. That was quickly found out to be something that is not yet to be prime time. As you can see in the middle there, we actually had to use 3 different aggregators, basically taking proprietary communications, doing a translation, sending it to another one, and then ultimately getting to our DERMS vendor, which in this case was Smarter Grid Solutions. Down at the bottom, you can see the battery system on that home. We used Sonnen batteries. We actually had to use their proprietary software all the way back to the DERMS. We couldn't get a translator for that. So there was a lot of technical limitations that we found. Some of those were identified in the bench testing that we initially conducted with EPRI at their labs. And then there were quite a few that were found later on in the field as we started to actually command and control devices. There we go. So the first section here is just it's just kind of a primer to show normal load and generation behavior. So we're all familiar with solar PV, and the power over on the left axis there, that is the power on a customer's home. So overall, this is that straight line in the middle would just be if there was no power being used at all. Obviously, solar PV is generating power, so this shows up as a negative on the overall graph. Then as we start to layer things in, you can kind of see how there's interactions just without any, this is doing no testing, this is just how things would work. Workplace EV chargers, a large amount of customers, employees come in the morning and they charge their cars, and then over time, depending on what type of car it is, there might be, there's definitely going to be a drop off as you get later on in the day. So you see that happening there. Then we have a typical HVAC system for a residential customer. So we just took basically the best fit line there of all of those averages from those 12 customers, and that's what you see in the brighter green there. Heat pump water heaters, as expected, this project was done basically during the middle of the year, a little bit in the spring, and then bled into the fall a little bit. Here in Arizona, we don't have a super great need for heating our water. Typically, at least during the middle of the summer, you can have groundwater that comes out at 80 to 85 degrees already. So we were expecting there to be a very small impact on heat pump water heaters, but this was really kind of telling that there's almost no load on those. So that was, as I said, that was just everything put together if there was no interactions, no control whatsoever. So as we started to look at the different devices, we had to kind of come up with a ranking system of what is it good for. So for example, to start, the battery energy storage system. You've got the likes and the dislikes over on the right side. The first two, can be dispatched in either direction or any time. They're not dependent on the sun. They're really dependent basically on their state of charge. To a customer, and a big piece of the project was just looking at what our comfort impact was. There's minimal impact for comfort. If your battery is in your garage, You probably don't know it unless you go outside to get in your car. One thing we did find is that our batteries were very loud. The air conditioners that were on them did have quite noisy fans, so that was about the only comfort impact that we saw. But then, as I mentioned, you must be aware of the state of charge on a battery. We did experience that where some of the battery systems actually, because they were going through the aggregators, there wasn't always the correct information being passed back about the state of charge, and we did almost brick at least one battery once by just not having it at a minimum state of charge for when we needed it. So that was definitely an eye-opening experience. Next, solar PV. Obviously, there's pretty much no comfort impact. And certainly, as I mentioned, all of these customers are receiving a financial benefit that is other than just net metering, because we own the systems and that power goes on our side of the meter. So even from a financial perspective, there was no impact. But the downsides, you can only curtail increasing load on the home, and our peak solar does not correlate with our utility peak here in Tucson, where we peak between 4:30 and 7:30 p.m. during the summers, and as expected, noon is the solar peak. So that's very difficult to try to hold that one in your back pocket for later in the day. HVAC, as I mentioned, we did smart thermostats. We used Ecobee thermostats for this project. We see here it's about 40% of the customer's load on average. Peak HVAC does correlate with the utility peak. It gets hot here in the afternoon, and so air conditioners turn on. So that is something that we can look to for managing customer load. There is a high customer impact, and that's both from a event loading, as you'll see in a little bit, also humidity, things like that some customers, depending on the age of their home, certainly experience more than others. So that was an eye-opening experience. And then finally, impact fades as the degree target is reached. Your air conditioners out there are all different makes and models, and they're pushing out air at different rates. So we would see that if you did an hour-long test, you may have fade starting in the 45-minute mark as air conditioners had to turn back on to just keep that target set point. So that was another very interesting find from this. Heat pump water heaters, again, minimal comfort impact. As long as you're making sure that there's water in those tanks, customers shouldn't have a big problem with it. But without having done a multi-year study, we really don't know what the predictable usage pattern is for customers, especially on a heat pump water heater, which is already very efficient, over a resistance coil water heater. So that there would have to be a little bit more research done. And certainly if we were to have done this during the winter time period, you would have seen more of an impact. However, you would have seen less an impact on other things such as heating and cooling. And then finally, at the bottom there, it really is only about 2.5% of a customer's load on average. So the incremental value of trying to control those is not always realized. Workplace EV charging stations. The usage aligns very well with PV generation, and since it's at a workplace, you can create programs for your employees so that they actually, so don't charge until say 10 o'clock, and then it soaks up that solar power during the middle of the day. But it is not available there to reduce the evening peak. A couple of our vehicles, fleet vehicles, would be there in the evening, but you couldn't always count that they would need a large charge up. So that was really not something that we found valuable. So taking all of those things into consideration, we created a matrix here of what would need to happen to each different type of device for it to basically achieve what's at the top there. So increasing load. So if you needed to soak up more solar in the middle of the day from your distribution circuit, or if there was a grid emergency or issue, you could decrease load. And so you can kind of see we only had one basically on the increased load, is just start taking as much power as you can to your different devices. But then we did, as part of the comfort and to see how we could affect things, we did have 3 different items, levels for the decreasing load. So you had shed, critical shed, and grid emergency. One of the things that I want to point out while you're looking at this is just in the middle there, the HVAC. So on the increased load, we had lowering the set point down to lowering the set point by 6 degrees. And so that's just essentially saying, hey, pre-cool the house as much as you possibly can. On the decreased load, this is where we started to see some big comfort impacts. 3 degrees, relaxing the set point, so say going from 75 during the summer and turning air conditioner on at 78. There was some comfort impacts to that, but not anything that we got any complaints about. But then when you would start to get customers who we would relax their set point by 6 degrees, that's when you would start to see issues, because we were doing testing anywhere from 1 to 2 hours. So if it was the middle of, if it was a June day, there's a good chance that they would be going from 75 to 81 and not expecting that, especially in cases where we did not do a load up on the air conditioners. So there wasn't a lot of pre-cooling done. So again, just kind of one of those things that as you actually take comfort and controllability into account when you're the utility, thinking about that, it could have been 2 degrees or 4 degrees. Those are all things that would actually, encourage a customer to stay with the program rather than just saying, hey, that was way too much. So the next couple of graphs as we round things out here is just an example of one of the events with preparatory load up. And when I say the load up, that's really just making sure that the systems are ready to go for whatever the 1 or 2 hour period is. And one thing I did want to mention that I forgot to at the beginning, all of these tests were done over the course of basically 153 different days. So we had in there was a variation of just testing days, baseline days. So just monitoring how the home acts during a day without any command and control, and then also actual testing days. So in this case, this event was a 2 hour event, and so you can see the window there. The first green bar here is just air conditioning load. So in this case, we did do a load up, and you can see that on the left side of the area that's marked as the event window, where you're basically dropping your air conditioner by 6 degrees. You're trying to super cool the house as much as you can, and then you're going into the actual event. As I mentioned before, you can see that there's some what we call snapback or degradation at about the end of the first hour mark, and then it goes down and does complete itself for the second hour. So that was HVAC. The next is the energy storage system. So again, loading up during the first hour and a half or so, 2 hours before the event actually happened. And the goal of all of this is to essentially get the customer's overall power usage down to as flat as possible and as low as possible. So you have the energy storage de-energizing or pushing itself back onto the grid during that time. Next, we have the heat pump water heater. So similar to the HVAC and the battery, there's a load up time at the very beginning, and then essentially no usage during that time of the event window, and then finally kicking back on into the evening and using itself just as normal. And ultimately, this is the sum of all the controlled devices. So at the same time, there's also the solar PV is doing its thing. So the battery storage is kind of working to mitigate that as well. So this is basically how we were able to flatten the loads or decrease the loads so the customer could still actually be comfortable in their home, and during that two hour event window, it's causing little to no impact on the grid if it were a grid emergency. So we did lots of different testing like this. What we came to, as I mentioned, are kind of some of the philosophical gaps. If you're working with an aggregator, they've got a obligation to the utility of reducing peak power demand. Also, system operations, as you've heard throughout the afternoon, But then there's also customer obligations. What's that customer convenience? Can they charge their car when they need to? Are they comfortable with whatever the set points are that you're actually changing their thermostats? So it does get to be quite a balancing act and something that will have to be strongly considered and thought of as more and more DERs are deployed, as DERMs are deployed. And again, it comes back to that question that's been asked a couple times. Is it better for the utility to do something like this or an aggregator? I don't know if we have an answer to that yet. So that is a really quick overview of Project RAIN. We did host 3 different technical advisory councils, and we've made those that information and those reports public. So there are some QR codes there. Hopefully these presentations get passed out and you'll be able to take a look at them and get a lot more details on things.
Excellent, Ted. Thank you so much for an interesting discussion. Appreciate the real world experiences that you're able to pass along. There were 2 quick questions, and we have about 5 minutes left in our window. One was from Vahaz Zamani. He asks, Ted, if you can elaborate on OpenADR.
Sure. So OpenADR is Open Advanced Demand Response. Essentially, it's a way to command and control devices in a demand response setting. So right now, we're not even advanced from a company as this project was. Our demand response programs are essentially, we send a text to a large customer and say, hey, can you please curtail a megawatt of power in the next half hour, and they have to go and do it. OpenADR just allows you to do that via an API or a cloud communication network.
Thank you, Ted. The last question was a general question from Rajiv Varma. He asks, he says, thanks for the great presentations, then asks in general about getting copies of the slides and the audio at some point in time. For that one, I will defer it to Ryan or Charlie. Do you want to answer on that? And maybe hold a second, because I think there's one more question that might be best for Ted first. Which is, did you consider more dynamic events for the study, like frequency regulation type events?
So we did not get into that level. We did, as part of this, deploy synchrophasers. So we do have some experience with how synchrophasers are bringing back information on the distribution grid. More of this was to just really see how we could get information back, you know, and working through those issues. We definitely were not there yet to do any kind of ancillary services.
Thank you. And then I see Tom Acker had a question as well. Ted, given your experience with RAIN, what main challenges do you perceive in the autonomous control concept that Ben presented earlier?
So as we were doing this, all of our batteries did have an autonomous mode, a set it and forget it mode. One of the things that we quickly found is that if you are deploying those with that turned on, there still definitely has to be some kind of feedback loop to say, are they actually doing the work that they're supposed to be doing? A good example of that is we had one battery that somehow it changed its time zone, and we could not get it set back. So it was doing everything just 8 hours later. And we worked with the manufacturer, and ultimately we did not get a good resolution. But that would be one of the things is you still need to make sure that what it's supposed to be doing is what it's doing.
That's great. I think we're out of time. I did see there were some other questions. I apologize to the people that we weren't able to get to. But Ryan and Charlie, I would like for you to provide any wrap-up that you have, possible.
Yeah, thank you, Steve. I think there was a question about the availability of the presentations, and Ryan is the wizard behind all of this, but the webinars are being recorded. They will be posted, and something will be sent out to all the attendees to let them know when and where. So thanks, everyone, for your participation. Thanks for your presentations. I should let you know that the next Tucson webinar is going to be on be session 5 on market design evolution for high share renewables. It will be held on next Thursday, April 9th at 3 p.m. Eastern. You can find the full schedule of the upcoming sessions on the ESIG website. So thanks again, stay safe, and we look forward to seeing you at the next session. Take care.